Okay, so welcome everyone to the One-Word-MINDS seminar today. So this is our second One-Mind seminar, One-Word-MINDS seminar in this alternative time slot. And so today it's my great pleasure to introduce Professor Man-Cho Anthony Su, who is currently a professor in the Department of Systems Engineering and Engineering Management at the Chinese University of Hong Kong. So he is also currently the Associate Dean in the Faculty of Engineering, Deputy Masters in Morningside College. And Professor Su is an expert in optimization who has made numerous contributions to convex and non-convex optimization with applications in signal processing, wireless communication, machine learning, game theory, etc. Professor Su is also is now serving and also have served on several editorial boards, including some journal on optimization, IEEE transaction signal processing, etc. So today he will talk about non-convex orthogonal group synchronization by the generalized power methods. So now let me give the stage to Professor Su.
Well, thank you, Shuyang, and thank you all for coming. It's great to meet you all online. It's a very unusual circumstances. I hope everyone is doing well and staying healthy and safe. It's my great honor to present this work here. Actually, a lot of experts are in the audience, and I'm also coming to learn from all of you. So this is a recent work. So actually, it's a couple works that we did on synchronization type problems. These are joint work with a couple of my former students, Hui Kang, Peng, Man-Cho, and Iterate. So maybe I would just start off with the background. So here we are interested in the orthogonal group. And so these are just square matrices satisfying the orthogonality constraint. And here we do not just focus on the orthogonal group itself, but also some of its closed subgroups. And I will give examples of them a little bit later, which one we can do and analyze. So here G, this calligraphic G will be a closed subgroup of this orthogonal group. And a typical task is the following. So you have a signal vector. So it looks like this. So each element is from the group. And so here, naturally, there will be matrices. And this is the ground truth which you want to estimate. And so what you have is the noisy measurements of the relative transforms. Here, Qi star, Qj star transpose is the relative transform of this. And so typically in the group synchronization literature, the relative transform is defined as Qi star, Qj star inverse. But of course, we are now working in the orthogonal group, so we can replace this by the transpose, okay? And so we have a collection of these noisy measurements. So I will indicate those pairs that I have by this index set E, okay? And so this is the set that I have. And so from these noisy measurements, of course, we would like to recover the ground truth using some methods. So this is the basic group synchronization problem, particularly in the context of the subgroups of orthogonal group. So this is an abstraction of many inverse problems in applications. So next, I will just give some examples. So for example, if you talk about the orthogonal group itself, there is a global registration of point clouds. So a problem that arises in computer graphics and vision. For the special orthogonal group, so these are the matrices with determinant equals to 1. So here, there are many applications as well. So for D equals to 2, this is also known as the phase synchronization problem. It has applications in phaseless reconstruction. In physics, they call it lensless imaging and rank aggregation and so on. For 3D SO3, then you have structure determination in the cryo-EM. So it is the imaging, and you want to reconstruct the molecule using rotations. So here, another one that is of great interest is the permutation group. So it is the OD, except that you require the entries to be 0 or 1. Right? So this is the permutation matrices. they have applications in matching. For example, even the hard problem of the graph isomorphism, you can think of it as you are trying to find a permutation matrix to map the vertices of one representation to another so that you can show that they are isomorphic. And here is to me is an interesting one. It's a cyclic group of order M. So usually one wouldn't write it in this way. So usually it is you write it 0, 1 up to n-1, and then the operation of the group is addition modulo M. And here actually you can embed it into the orthogonal group of 2 dimensions by writing it out using this representation. Basically, this defines a graph group isomorphism, and so you can the usual addition operation in the cyclic group becomes multiplication in this matrices, and the validity of this is just by the very standard trigonometric formulas that we learned in high school, right? In this problem, for example, when m equals to 2, this has been extensively studied in community detection, for example, with 2 communities. For general M, this has been studied in this paper by Chen and Candace with joint alignment. So there are many applications. Of course, these are all abstractions. In practice, there are, of course, other considerations, but this is a good model for modeling a good number of different problems. So here is a common approach. One would formulate this kind of least squares formulation. So here, this is rather natural. So Cij is your measurements. They are noisy. So you want to find the group elements. So you want to recover the ground truth so that this is as close as possible. And so if you use the fact that our group is actually a subgroup of the orthogonal group, and you expand this out, so you can turn it into a maximization problem, and you can write it compactly in terms of this maximization problem. So here you can see that we basically combine all these elements Q1 up to Qn. We write it in a long column. It is, we look at this as ND by D matrix. So each of them is D by D, and then I stack it up. So then you have an ND by D thing, okay? And C here is a matrix that you can construct from this Cij. It is just by writing it out. So I won't write out the details here, just that it is, I guess, intuitive and natural. One can show that you can construct such a C, all right? Now, so we have this formulation. So this is the least squares formulation. By no means this is the only formulations that we can use. Of course, there are other ones motivated by different considerations in practice, such as robustness and so on. But this is, I guess, a classic one. So we will start with this. And so this is non-convex in general. Typically, for example, the objective function is a quadratic in Q. This could be non-convex. And of course, the constraints themselves are already non-convex. However, this possesses quite some nice structure. And so one may hope that one can avoid the curse of the NP hardness, so to speak, and devise some methods to tackle this. So of course, if you think of this in the worst case, this will be NP hard. But for example, it has several nice features. It has a quadratic objective. So this is a homogeneous quadratic. If you think about the group as OD or SOD, then this is a product of manifolds. So it gives you a flavor of a manifold optimization problem. One may use manifold optimization techniques to tackle it. And what is more, and this is usually the key thing in the existing literature, and that is the measurement matrix is not arbitrary, but it usually comes from some sort of generative model. And so with this, then your data are not worst case, but are in some sense random. And so there is a hope that you can tackle this problem effectively. So let me briefly now review some of the existing efforts and attempts to tackle this formulation. And give a brief comment on why we want to do more. And so one of the first line of approaches that appear earlier on, and some of the people in the audience are also contributors of, is the semi-definite relaxation. And so this having this quadratic form and also this orthogonal group constraint, it is very natural. One can think of various semi-definite relaxation schemes for this. And so when you do this, this will be polynomial time solvable. And under various generative models, they enjoy very strong recovery guarantees. And so there is a long line of work. And here, if I miss your reference, so forgive me. So these are just some of them that I come across. And then also, and so these there are many strong recovery guarantees. And in various cases, they achieve either the information theoretic optimal or are very close to it. Now, however, as we are now in this stage in 2020, so we are moving more towards first order methods. And so one common complaint about the SDR is that, of course, it doesn't scale very well with problem size. And especially with these big matrices, when you do the lifting, the problem becomes quite large. And so this there is another approach, and so people start looking into non-convex approaches into this problem. For example, Bura-Montero approach is something very popular in recent years, and basically it is a low-rank version of the SDR. So you basically impose implicitly a rank constraint on the variable by factorizing the matrix variable in the SDR. And so you try to solve that. So you basically enforce the low rank constraint implicitly. And so a lot of them, they can be solved by manifold optimization algorithms. And they define smooth manifolds, the constraints, so you can do that this way. However, as far as the recovery guarantees are concerned, they are slightly weaker than the SDR approach. So it is still ongoing effort to try to fully recover the recovery guarantees of, for example, the SDR approach. Here, I would also like to comment on the manifold optimization algorithms. And so here, for example, one method that has been commonly used is the RTR, the Riemannian trust region method. And usually so far there hasn't been so much effort going into analyzing its complexity when you are tackling this synchronization problem. Of course, there are worst case iteration complexity guarantees. Now, however, they are for general problems and for this very structured synchronization problems. So far as I know, there are no sharper complexity analysis for this kind of methods. And so this is also an interesting issue because, for example, can you achieve better than sublinear convergence with this kind of problems? That would be an interesting issue. Of course, that would be a more optimization related problem rather than a estimation related problem. So here, when we are talking about recovery guarantees, it is more of the estimation side rather than the optimization side. Okay. And so a third type is spectral relaxation. So basically using spectral methods. So these are very simple and efficient methods. So you just grab a suitably constructed matrix from your data and then compute certain eigenvectors, and then that's it. All right. Very easy, simple, and efficient to implement. And in many cases, they already achieve pretty good performance in terms of estimation. So one can prove that they are already within a certain distance of the ground truth signal that you are trying to estimate. Now, however, of course, so being simple, that means you can also improve their estimation performance by performing more local moves. For example, you use it to initialize certain gradient descent method, and then you perform descent. Usually, you can prove that you can achieve better estimation performance. But this also says that you can use this as an initialization for various other methods, and this is also widely used in the literature. Now, so those are the three types of methods. And so here I'm going to introduce another one, which is the main topic of this talk, which is the generalized power method. And in some sense, popularized in these two papers that one is dealing with a manifold or PCA type problem, and then the paper by Bumo is on phase synchronization. So this is very similar to a projected gradient type method. So you basically take a gradient step and then you project back to the constraint. And so, of course, it has some connection to the classic power method, and that is why it is termed generalized power method. So let us examine this in the context of the problem we want to study. So here is the orthogonal group synchronization problem again. So here again, G could be a subgroup of the orthogonal group. And so for this, basically the generalized power method goes like this. So I have the measurement matrix C. So this is the one I construct, and I need to initialize it somehow. And then what I do is basically I compute the gradient. So here CQ is essentially the gradient of this function, and then I project it back. Okay, and that's it. And so it is very simple to describe. And so, of course, the efficiency of this method would depend on, of course, first of all, you need to compute this product, and also how efficient you can project onto this product of groups that you have. But in terms of the description, this is it. So let me comment on a little bit about on this implementation of this algorithm. So first of all, the projection, because of this product structure of the group, so you can compute it blockwise. So here, the gradient you compute will be an ND by D matrix. And so you can naturally divide it into N D by D blocks, and then you basically do the projection blockwise. Okay, so projecting onto Gn, the product of the group reduces to whether you can compute the projection into the group efficiently. Okay, and so for various choices of the group G, so actually the projector can be implemented efficiently, even though the group may be non-convex, or the set that define the group may be non-convex. And so here we are just being brave, right? Usually we think of projection as working well on convex sets, right? So if you're familiar, remember from your convex analysis, projecting on a closed convex set, you have a unique point, and it is always uniquely defined. But there is nothing that stops us from projecting onto a non-convex set. We can still do it as long as we can do it efficiently. And it turns out for the groups that I introduced earlier, they can be done efficiently. For example, for the orthogonal group and SOD, this is rather classic as well. You can do SVD and then manipulate it a little bit. You get the projection. For the permutation group, basically it will come out like an assignment problem. So you can solve it like a linear program. And for the cyclic group, ZM, actually you can write it in closed form. So that is even better. So you just need to evaluate certain trigonometric functions, and then you can compute the projection in closed form. And so now, and another point is, I mentioned that this is like a projected gradient method. So if you are careful, you would say, well, the classic projected gradient should be, I start at my current iterate QT, and then because I'm maximizing, I will do ascent. So I add the gradient, so QT, and then plus a step size times the gradient. And here, it should more be of this form, right? So this is the typical projected gradient step. So it is QT plus alpha t times the gradient. So here, I didn't do the QT in front. I just directly project this. And in some sense, you can think of this as I'm just taking the step size to infinity. This has a stronger interpretation in some of the synchronization problems that have been studied. For example, the phase synchronization, this really looks like this. And so here we just take the idea and then we pretend that the alpha t goes to infinity. And so the projection here, we just do it this way, okay? So that is the scheme. So in terms of the correspondence to the projected gradient method and also the implementation of the projection, I hope I explained that clearly. So if you have questions, please do ask. But as I said, the algorithm is rather intuitive and straightforward. Now, of course, the thing is that, of course, you want to analyze it a little bit. And so what is its performance? And so what are the questions of interest with regard to this algorithm? Now, so of course, our original problem is hard in general. It is non-convex. So if you want to have some results regarding the performance, we probably want to have a generative model of the measurement matrix. So one typically adopted one is the additive noise model, look like this. So the CIJ, previously I just say that this is a noisy version of this. So now I'm being specific on what form it takes. Okay, so here it takes the form of an additive noise model. So here I'm adding to it. So a noise matrix. So eta ij is a noise matrix. And so when we do the analysis, we will assume further statistical properties on this guy. All right. And so this is the additive noise model that we are considering. And so under this model of the data, so CIJ is our data. And of course, from that, it induced the big block matrix C that we discussed earlier. So this guy, C, okay. And so we have basically the following questions that we need to answer. So first of all, for the GPM, it is projected gradient method. And so the performance, as you can imagine, would depend on the initialization. After all, we are doing a non-convex problem. And so how do we initialize it so that it has good performance? That is the first question. The second one is the estimation performance. This is related to the noise model that we assume. So this is more on the statistical side of the problem. And that is, suppose I take the tth iterate. So here small t is the iteration counter. And so how far is it from my ground truth? So I will always use star to denote the ground truth. Okay. So how far is it from the ground truth? So does it improve as t goes on? So that is the estimation performance. And finally, from an optimization perspective, we are interested also in its convergence performance. So in particular, does the method converge? All right. If it does, what point does it converge to? Is it a local minimum, maximum? Is it a global maximum, or what point? And if we can resolve that, we can also be a little bit more greedy and ask at what rate, what is the convergence rate? Okay, and so these are a series of questions that you can pose once you have this algorithm in mind. So here, let me present our main results for this. And so just a spoiler alert, we won't be able to resolve all the questions that we pose, but we will be able to answer at least the first two. And for the convergence, it is still open. Okay, so that is where we are heading. But I will present to you how we resolve the first two. Okay. Now, so to set up, we need a little bit of terminologies and also quantities. And so first of all, I need to define the estimation error that would be used for discussing our estimation performance. So we want to know how far Qt is from Q star. So we need a measure for it. So our measure is this epsilon measure. The motivation for this is that actually this objective function is invariant under global right group action. So actually, because of the relative transforms that you get, actually you won't be able to exactly recover the ground truth. You can, at best, you can recover it up to a global right group action. Okay, and so here we allowed ourselves to have a global right group action acting on the ground truth. And so the minimum one, we will define this as the estimation error. Okay, so just a reminder, QQ star, they are ND by D matrices. So you can think of them as N blocks of D by D matrices. And U here is a group element, so it is D by D. And here we can also, from our measurement set, we can define a graph, right? A measurement graph. So remember, Y is the set of measurements that we have. So we don't necessarily measure all the pairwise relative transforms. We only measure a subset. So Y here is the set we measure. And so that naturally defines a graph. So you have an edge there whenever you measure that relative transform. And so you can think of Wij as being the weight assigned to the edge. Here, though, I have a little addition there. So I also include self loops in this graph. Okay, so here the Wij equals 1 if I equals to j. So besides the ones that you measure, I also include the self loops. Okay, so this is just for later analysis. And so you can then define the degree of the ith signal element. So in this measurement graph, the nodes are the elements that you want to estimate. So Q1 up to Qn. So you have n nodes. And then the degree of the signal element is just you sum up all these weights, and that would be denoted as Ri. Okay, so and so in some sense, if you have complete measurements, so if you have n nodes, you have complete measurements, so Ri will be equal to n. Okay, so for all I, so because it includes your n minus 1 neighbors and the self loop to yourself, so Ri will be equal to n. Okay, so that is the notation. And also, we will define this noise matrix. So this is essentially eta ij, right? If you look at our noise model, Cij is Qi star Qj star transpose plus the eta ij. So you can just think of this as eta ij, and we just group the noise in this big block matrix. Okay. So with this preparation, then we can discuss our master theorem. So this is a very long thing, so I will go slowly. So basically, let me go one level at a time. From the top level, it reads like this. Okay, so you look at the iterates generated by the GPM. Okay, so you need 4 assumptions. So here are 4 assumptions. And so I will discuss this assumption later. So one of them is very intuitive, right? You should initialize it properly, but there are other ones as well. So there are 4 assumptions. Once you satisfy all these 4 assumptions, then your estimation error will be bounded like this, okay? Now, let us take a look at this expression first. There is a term that would decay geometrically to 0. So this is some fraction raised to the t plus 1. This is the estimation error of your initializer. But then there will be a part that you cannot get rid. So this, you can think of it as the inherent estimation error because of the noise. So this will depend on some parameters, so which we would then need to go back and introduce. Okay. Now, so the basic message of the error will be like this. Now, so what are the assumptions that you need? Okay. Now, so I already explained the 4th. This is very natural. You are using GPM. It is a non-convex problem, and so it would depend on a good initialization. So your initial point should not be too far away. Okay, so it should be on this order. But then it involves a rho. So what is this parameter rho? Okay. Now, intuitively also, your estimation error should also depend on the nature of the group. Right? So here we are not only focusing on the orthogonal group, but also on various subgroups, and they can be of very different structure. As the examples that I showed you already, some are even discrete. Some are, for example, nicer like SOD. They have a manifold structure. And so in some sense, the estimation should also depend on the geometry of the group. And so how does the geometry comes in? And this is the first point. Okay. So the first point is that basically you characterize the geometry in terms of the projector. Okay, so here is the projector onto the group. As we said, the projector can be easily computed for several of the ones that we introduced. And so here, the left-hand side is, so first of all, X is in the convex hull of G. Okay, so you have a manifold, you take the convex hull. And then, so this is measuring the distance of X to the group. Okay, so this is basically measuring the projection distance. And so this projection distance can be estimated by this quantity. Okay, so this is the idea. So here you can think of this as a surrogate measure of the distance to the group. And in particular, if X itself is already in the group, okay, then X transpose X is the identity. So this will be 0. And so your distance to the group will also be 0. Okay. However, of course, this is not the distance. So this is just an estimate. So this is a surrogate. All right. And so we characterize the geometry using this, what we call a residual function. So basically, if x is in G, then this is 0. But if x is not in G, then this will serve as an estimate of the distance of x to the group. All right. And so how are we going to apply this? Basically, we will apply it to the iterates of this form. So this is actually in the convex hull of the group. And so basically, we will put it there. But the key here is we want this inequality. Now, what else would you need, right? So here I allow myself to have incomplete measurement set, right? I allow myself to have incomplete sampling. So naturally, if I sample too few, then I probably won't be able to recover the ground truth, and that is intuitive. And so here, and why this is informal is that this sentence in italics, I just briefly describe what it is, because to fully introduce this, I will need to introduce a lot of parameters, which is a little bit tedious, okay? So let us just say that we have a sampling requirement, and so that means you need to sample sufficient pairs in order to do the reconstruction. And I will be more specific in a moment how dense this needs to be under various sampling model. Yeah. So here, okay, there is a question of why X is required to be in the convex hull. Yeah, and that is because ultimately I want to apply this inequality to this object. Okay, so this object here, xt, is obtained from the teeth iterate of the GPM. So Qt is the teeth iterate of the GPM. And so this guy is not necessarily in the group, but if you write it out, remember Q star and Qt, they are block matrices. They are n d by d blocks, okay? So it is not just a single one, okay? So these are n d by d blocks, and when you multiply it out, you see that this is exactly in the convex hull of the group, okay? And so that is why we need this for all x in the convex hull. Yeah, but of course, since I will not be discussing the proofs, you may not see the importance of this in the slides. But if you refer to the paper, then you will see that in the derivation that we will need to study this object. Yeah. So I hope that answered your question. All right. So we just explained the second requirement. The right-hand side of G. You can think of it as a linearization, but of course, I would like to think of it as a surrogate measure. Because in general, I don't necessarily need a linear surrogate measure. It can be anything as long as it is easily computable. In some sense, this may not be easily computable, but this may be more better, more accessible. So I will use this. And I will come back to this later when we talk about convergence analysis. So we are basically constructing surrogate functions of the distance. Yeah. All right. And the third one is also natural in terms of why we need it, because if it is very noisy, if your measurements are very noisy, you wouldn't expect that you can recover your ground truth well. So here we have some conditions on the noise matrices. So here delta is the noise matrix that we construct from the ADA blocks, and it needs to be sufficiently small in some sense. Now, so to appreciate the order of this kind of things, so let us take a look at what D is. D is this block diagonal matrix, basically R1, R2, and then up to Rn. Remember what R1 up to Rn are. They are the degrees of the measurement graph with the self loop. So let us think of a simpler case where you have the complete set of measurements. Then R1 equals to R2 equals to Rn. They all equal to n. And so the inverse is basically 1 over n. And so when you have a complete set of measurements, basically this requires the operator norm of this noise block matrix is of order n. Okay, so that is what it means. But here, we can be a little bit more flexible because we are allowed to have incomplete set of measurements. And so we also have this part, and it is similar that you control the noise of the noise power, basically. All right, so this, I hope, explain the 4 assumptions. Now, and then we have this conclusion, okay? Now, of course, then this is the master theorem. And the next natural question is, can these assumptions be satisfied, right? If they cannot, then this is just, just a dream, right? So this theorem is not of much use. So in fact, one can verify it for the subgroups that we mentioned earlier. And so here are some of the subgroups that we have. So as I already mentioned, this function is a residual function. In the optimization literature, we sometimes refer to this as the error bound. So basically, it bounds the error between x and the target set you want, which is G. Okay, and so this is the residual function, and we need the existence of rho. Actually, this part is extraneous. This is typo. So we need a constant rho that satisfy this. So what is rho for the particular groups we think about? So for OD, SOD, the permutation group, and Z2, actually one can prove that rho is just equal to 1. So this you can prove. And for Zm, when m is bigger than or equal to 3, it is this quantity. So basically related to the sign of pi over m. Okay, so one can prove this. So this take care of the first condition. Now for the remaining ones, then you will need to work on it a little bit. And so you need to, for example, assume how your measurement graph is obtained. And so, for example, if your measurement set is induced by the classic random graph model, the Erdős-Rényi, then basically we need a parameter of, so you have an edge with probability at least 1 over square root of n. Okay, and so from the random graph theory, at this level, the graph will be connected with very high probability already. And so this is the level that we need. So P should be like this. So again, what is P? P is the probability that an edge appears between a pair. And so all the edges are independently sampled with this probability P. And then we also need to assume what the noise matrices look like. So for simplicity here, let us just take them to be Gaussian random variables. So each of the entries are IID Gaussian with the noise level bounded by square root P times n minus 1. All right. And so this gives you a whole range of parameters that you can play with. So for example, if P equals to 1, that means you sample everything. Then your noise matrices the noise standard deviation can go up to roughly square root n. But if you have incomplete set, then the noise that you can tolerate is also smaller. Okay, and so under these parameters, you can also verify that the two requirements are satisfied. And so moreover, how do we get the initialization? Well, again, this is also classic. It is you use some sort of spectral estimator. Here, the one that we use is we take C, and then we basically compute its eigenvectors and then put it in a column. All right, and then so after you do that, you project it back onto the GN so as to get a feasible solution to start. That is our spectral estimator. And with this, one can also prove that it satisfies the requirement that we impose, which is that it is within square root of n divided by 2 rho of the ground truth. Okay, so these are the results basically. And so what is, as I mentioned already, the estimation error basically will decrease geometrically to something that you cannot get rid. So if we go back, so here this part will go to 0, the first term will go to 0, but this is a part that you won't be able to get rid. So this is in some sense one can think of it as the inherent estimation error. I should comment on that. This part also appears in earlier works on the phase synchronization problem. So when you estimate this, so there is also this part that is there, and it is of information theoretic in nature. And so what is the key to the proof of this master theorem? So it works for any subgroups of the orthogonal group if you can verify the 4 assumptions. And so the key of the proof is this contraction-like properties. And this is and this property seems to be quite central from our experience with the GPM. And that is, if you look at the projector, now, if it is projecting onto a convex set, I think most of you know that the projector is non-expansive, meaning if you project, it is less than or equal to 1 times the unprojected point, right? So a projector is non-expansive operator. Here, but we are projecting onto a non-convex set, still, it is almost non-expansive. So you basically pay a factor of 2. And so this is the key result. And it appears that this come back again and again in different analysis of the GPM for different problems. And so somehow this is quite an interesting property for analyzing the GPM. Now, however, there is one also. Yes.
Oh, Anthony, can I interrupt? Sorry. So there's a question. So Matthias Luther is asking if the statistical term in the bound, whether the constant is 16/3 is the right constant, or right? Don't we know about optimality of that term?
Definitely, it is not optimal. So I would comment on this in a moment as well. Yeah. So this is just for convenience of the analysis, but as I would comment in a moment, the whole thing, even whether the orders are correct. For example, here I impose this kind of order, right? So square root n and so on, and then this is what we can prove with this kind of statistical models. Whether these are of the right order, to jump ahead a little bit, I believe they are not. Okay, they could be improved, I'm sure. But the thing here is it is a unified approach for analyzing subgroups of the orthogonal group that satisfies these 4 properties. Yeah, so that is definitely one thing that one could work on, and this is definitely worth pursuing. Yeah. So, but I will come back to this in a moment. Yeah. So the next point I want to make here is of optimization nature. Now, so far, what we have been discussing are all statistical in nature. So we have a noise model. We say that how far is the iterate is from the ground truth. And so we use this epsilon measure. And so we know that the estimation error decreases. It will stay, there is an upper bound is this, and that's it. Now, in the process, in this theorem, what we didn't say is whether the method converges or not. So actually, the method may not converge, but then you still have this estimation error bound because this is true for any iterate, right? So you can stop it in the middle at any time, and you will get a bound of this form. And so here, and that is why I said earlier that we didn't resolve all 3 questions that we originally posed. So the 3 questions are, again, the initialization, the estimation performance, and the optimization performance. So roughly, the master theorem resolved the first 2, although may not be in the optimal way, but at least it gives some answers to those. But from the optimization perspective, we really have no idea. All right. And so here, we didn't say whether it converges or not, and we don't need it anyway, right? Because if we are just looking at estimation performance, whether it converges or not is irrelevant because we have already this estimation error band. Okay, so it decreases. So then naturally, there are these issues for further study, and that is where I will come back on to the optimality question. So here, the estimation error bound is, in my opinion, most probably suboptimal and can potentially be improved using the leave one out technique that have been used quite successfully in various settings already. And so here are the 3 recent work that have applied this technique and quite successfully get a very good estimation error bounds. And so I would expect that, so even without the constant, whether the terms can be improved, and my answer to that, if I need to guess, I would say most probably you can. Yeah. Now, but the crucial question, so as an optimizer, is the convergence performance as well. So if we are looking at this as an optimization problem, can we prove convergence, right? And if so, what kind of points does it converge to? And more ambitiously, at what rate, okay? Now, we don't have a answer to this question yet, although we have some results for special cases. And so here, what is going next is I'm going to share with you our result for the special case of phase synchronization. Okay. But before I go there, are there any quick questions on this part? Or we can save it till the end. All right, let us move on then. So here are the convergence results for the special case. Oh, yes. There's a question. Okay, maybe
there was no questions, at least not that were publicly stated.
Yeah. But yeah,
I privately. Okay, then yeah, go ahead.
Yeah, and then I will come back to this. All right. So here is the phase synchronization problem written in a more compact form, I guess.
Anthony, sorry, I think Nikolai has a question. I'm gonna unmute him.
Okay. Yeah.
Second.
Okay. Thank you. Sorry. Yeah. Can you hear me now?
Yes, I can hear you.
Can you hear me now? Okay. Fantastic.
Yes.
Thank you. Hey, Anthony.
Hey,
so yeah, I had a quick question on slide 14, just since we're roughly on those topics. So just one slide back.
One slide back. This one.
Yes, this one. So I'm looking at the top of the slide there. So you have this row equals 1 for all these groups, but then for ZM, row grows with M, right? If M is larger, then row is going to be larger. And I was wondering, this is a bit surprising since for SO2, which is the continuous limit, row is equal to 1. So can we understand why row explodes here?
Yes. Thank you for this is a very good observation. Yes, actually we are actually puzzled about this as well. So when we do the construction, we actually have examples to achieve this bound. But then when we increase M, the example also increase in dimensions in some sense. In some sense, there are two, how to say, so there are two parameters that are varying at the same time. So it is not straightforward that the SO2 is the limit of this guy. Yeah. So but that is a very good observation. Yes, we are also puzzled by this for a long time. But for each of the finite M, we do have a construction that achieves this row. Yeah. But then there are multiple parameters that are varying. So as they go to infinity, it's not clear that the limit is the SO2. Yeah. So yeah.
Thank you.
Yeah, I hope that gives you enough to understand.
Yeah, absolutely.
Yeah, thank you.
Thank you.
All right. And then so in the noise, yeah. So here the right group action is the most obvious one that is that would cause the ambiguity here. So that is the best you can do. The other ones probably would be caused by the noise, right? So in the noiseless case, I think the global right group action is the one that would cause the ambiguity. Yeah, I think so. All right. Let me continue and go back to the phase synchronization problem. So this is again the SO2, but then of course we can also represent it. So here, this is the interesting thing about this group synchronization problem. You have various different representations, and here we can change the representation using complex numbers, and you can also represent it like this. So basically, you have a phase that represents the rotation angle. And so this is the classic setup. So basically your ground truth look like this. You have a rank 1 complex matrix plus a Hermitian noise matrix. Okay, and so this is your measurement matrix. Here, for simplicity, let us assume that we have a complete set of measurements. Okay, and so the least squares formulation for this, you can write it out, and then it turned out to be a quadratic optimization problem. You are maximizing this complex quadratic form subject to this torus constraint. Again, the torus is this n-dimensional complex vectors where every entry has modulus 1. Okay, so again, this you can of course write it as a quadratic constraint. Basically, it is saying z1 modulus square is equal to 1. So these are all quadratic constraints. So this fall into the realm of quadratically constrained quadratic programs. Again, a very natural way to tackle it is the semi-definite relaxation. But here we are going to try something different, which is the GPM. Okay, so again, this already appears in Nicholas' paper, and so this is roughly how it goes. So here we include the step size here, and the reason I will explain it in a moment. So here we are at ZT, and then we are doing basically gradient ascent. So we add the gradient and then project it back to the torus. And projecting back on the torus is easy. Basically, they are complex circles. Again, you can do it block-wise or component-wise. And then basically, you are just pulling your point back to the rim of the complex circle. So this is quite easy. And for the initial point here, there is a very standard way. Is again the spectral estimator. Basically, take the measurement matrix dominant eigenvector. Then you will, it can serve as a initial point. And this has been studied earlier on, I think as far back as 2011 by Amit Singer. So this works quite well already. So here is our convergence analysis. So this appears in a paper earlier. So this is the problem we want to analyze. So, and here again, the function is invariant under multiplication of a common phase. So meaning you can multiply by e to the I theta to the variable, and then it will still give you the same thing in terms of objective value. And so this is the measure of how far 2 points are on the torus under this objective function. And so what you can prove, basically by combining the analysis we did in this paper with the probabilistic bound using the leave-one-out technique later in this paper in 2018, essentially one can prove the following result. Okay, so what is the result? So let us go one by one. So the noise matrix is essentially a Wigner matrix. So the entries are IID standard complex Gaussian, and then you multiply by a sigma. So sigma can go up to this level, square root n divided by log n. So this is the bound developed in this paper by Zhong and Bumo. And then you choose a step size of the same order. Then you will have these two conclusions. Okay, so what are they? So here, Z hat is the optimizer. All right, so it could be different from Z star. So don't confuse the two, right? The optimal solution to the problem can be different from the ground truth because one can be corrupted by noise. So here Z hat is the optimal value. ZT is the objective value at the teeth iterate. And so basically this will converge linearly in the iteration counter t. So lambda here is some constant that is between 0 and 1. It can be given explicitly, so it is done in the paper, but here let us simplify it and just write it as lambda. And so basically it converges what we call linearly. So it is basically geometrically decaying to 0. And not only the objective value converges linearly. So in estimation problems, usually you don't care so much about the objective value because it is just a surrogate for helping you to find the ground truth. What is more interesting would be the iterate convergence. And so here, the teeth iterate, the distance of the teeth iterate to the optimal solution is also converging linearly. All right. And so basically it says that in not too many steps, you will be able to find the optimal solution to this problem, which using prior work, basically you can show that this is also equal to the ground truth. So Z hat actually under this kind of parameters, it is also equal to the ground truth. Okay, now so this is one can prove. So what is the key technology here? So let me briefly mention. And so this is what I am very interested in terms of analyzing the convergence or the optimization performance of this kind of methods. And so the key is, again, this what we call error bounds. And error bounds is basically an inequality that bounds the distance to the target set by some surrogate. Okay, and so here our error bound is like this. So given any z that is close enough to the ground truth. So this is the condition. So that is why it is local. You need to be close enough to the ground truth. Then the distance to the optimal solution can be estimated by this function. So what is this function? So it is given here. So sigma z is this function, which is the diagonal of, so I'm putting the modulus of the entries of this vector onto the diagonal and then subtract by C tilde. And what is this C tilde? It is your measurement matrix plus the n divided by alpha I. So this is kind of like the step size that we take in the GPM. Now, so this is the error bound. Now, so why do I come up with this thing, right? So at this point, it is totally a mystery. But here you can see that the left-hand side is what you want to estimate, right? Because given any point, if you can compute how far it is to the optimal solution to your problem, that would be a major bonus, right? However, computing this distance often requires you to solve the optimization problem itself. So the left-hand side is not very, it's not essentially, it's not computable, right? And so that is why we want some surrogate on the right-hand side. And so that is the spirit of error bound. So you have something that is hard to estimate. The target is I want to estimate the distance to the optimal solution set. Can I find some surrogate measure that can estimate this distance? Now, with this in mind, the next question is, why do I want to use this surrogate? And this is because of the following result. And this is already shown in Nicholas' earlier paper. Basically, every second order critical point, so satisfying the first order and second order optimality conditions, they will necessarily satisfy this identity. Basically, if you plug in sigma z tilde and then multiply by z tilde, it should be 0. And it appears here, okay? Now, so if you think about it, if z is optimal, then of course it is a second order critical point, then this will be 0. And so that means the right-hand side will be 0. And so this checks out because then your distance to the optimal point is also 0. Okay, so this checks out. But then this function allows you to move a little bit away from the optimal solution set and characterize the distance of the points in the neighborhood of the optimal solution by this surrogate function. Okay. Now, so this goes back to an earlier question asked by one of the audience, and that is, do we necessarily need to use linear functions as surrogate? And as you can see here, this is not necessarily a linearization of this distance. Okay, so this is constructed from the optimality condition of the problem. All right, and so we use this result to construct this surrogate. But then the hard part is you need to prove that this inequality actually is valid. Okay, and this is the major part of the work. So, but once you have this error bound, and if you are familiar with this convergence analysis template using error bound, so I think some of you in the audience, you may be familiar with the so-called Loeschewitz inequality or the PL inequality. So that is the similar thing in spirit, right? So basically, once you have the Loeschewitz inequality of this error bound, then combining with the algorithm properties, then you can essentially establish the linear convergence of the method. Okay, so here this is the key technology that enable us to prove the linear convergence. Now, however, for the general orthogonal group synchronization, we still don't know how to do this. Okay, so this is the difficult part. All right. So with that, I think time is also short. So let me close with some further thoughts. So actually, the GPM is rather versatile and can be adapted to other problems, not necessarily of the synchronization type, although it can be. So here are two projects that we have worked on. And so also we can show that the GPM is actually working quite well on this non-convex problems. The first one is from signal processing. It is a very classic problem, the Mimo detection problem, multiple in, multiple out. And so it is essentially this discrete least squares problem. Okay, so here H is the Mimo channel. So multiple input, multiple output. So basically the antenna. So H is m by n. Then n is the input number of antenna, and m, the number of rows, is the number of output antenna. And so you are sending this message to your friend X, and then it goes through this channel, and your friend will receive Y. And so you want to decode what X is. Okay. And so in the signal processing community, X is usually coming from a constellation, so usually a discrete set. So you can think of them as code words. So this could be either the so-called QAM constellation. Basically, X, every entry will be a complex number, and the complex number has real part and imaginary part drawn from this collection. So it is either +1, -1, plus or -3, and so on. So this is what is known as the QAM. The other one that is more intuitive is the MPSK. This is just the mth roots of unity. So this is the roots of unity on the complex circle. Okay, and so one can formulate this. And we actually applied the GPM type algorithm. So again, a projected gradient descent or ascent onto this. And one can prove the finite convergence of the method under certain statistical assumption on the channel. Okay, so this is also what one can prove. So this is from the this paper, so on large scale Mimo detection. Another one, which is a more recent work, and we revisit the community recovery problem in the stochastic block model. So this has been studied for a long time. And so here is one maximum likelihood formulation. It is a quadratic maximization problem. Here A essentially comes from the adjacency matrix of the stochastic block model. Here we are only considering two balanced communities, so two communities of the same size. So basically that is why we have this constraint. E transpose X is 0. E is the vector of all ones. So basically X, each entry is ±1. So the add up has to be 0. So X has the same number of 1 and -1. Okay. And so for this, we also managed to analyze the GPM, the generalized power method. So this is a little bit more involved. It has to have an initialization stage and then followed by the GPM type stage. So two-stage method. And so we analyze its complexity. And so one can also establish its optimal recovery guarantee. So basically with the GPM, one can achieve recovery down to the information theoretic limit as well. So we resolve both the estimation performance and the optimization performance of the GPM for this problem in this paper, in this recent paper. Yeah. So this is a rather interesting method. It works in quite different and many settings. Again, one of the key to proving this or to analyze this method, basically there are two. One is the contraction type property that I mentioned earlier regarding the projection. So although you are projecting onto non-convex sets, do you still have a good control on the Lipschitz constant of the projection? That is one. And the second is if you want to analyze the convergence behavior of the method. So the error bound that I just introduced is also a very useful technical tool for doing this. Okay, so with that, thank you all for your attention. So that is all I have. So I would be happy to answer any questions that you may have.
Okay, thanks, Anthony, for the great talk. So any questions? You can basically unmute yourself if you have a long question. Okay, so let me start one question. So I have a question in the contraction. So basically project the matrix. So it's in the previous slides. So you project the matrix to the group set and it has the R's parameter in the column. Yeah, this one. So this R is arbitrary or like
so this can be for any R. So we need this because in our analysis we need to do some scaling for this matrix as well.
I see.
Yeah. So one hint of where this might be needed is coming from here. So
okay.
If you plug in this guy as x in this inequality, so you will see 1 over. So this is identity, and then minus. Basically, you have 1 over n times this guy, right? And so this is the factor 1 over n, or if you multiply it on the other side, that it will be n. Then that is what we need here in this. That is the R basically.
I see.
Yeah. So that is why we need this factor. Yeah.
For general, yeah, it's
Well, of
true
course,
for any R.
yeah, of course, if you want to connect it to the usual contraction property, then you take R equals to 1. This is also okay. So that is yeah. So that is the usual contraction type property.
Yeah. Yeah. Nicola has a question.
Yeah. So yes, that is a big hurdle indeed. Yes, that is exactly the right observation. When we do this, all the hard part is on the commutativity. So even coming up with the estimation result, we need to somehow bypass the non-commutativity issue when you move on to a general orthogonal group. Yes, that is correct. Absolutely. Yeah.
Okay, thanks.
Yeah.
So is there like a specific identified place where you had to do something about losing commutativity, or is it sort of all over the place and I should just go to the paper?
There are a couple places. In fact, it starts off with this contraction type property. It already needs a little bit handling. But this one is, I guess, easier to handle. The proof of this proposition is not too long, so this can be handled. But there are also other places that one will need. But one would start from here, basically. Yeah.
Okay, thanks.
Yeah. Yeah. So, but the current thing that we don't know is whether the non-commutativity is also a hurdle for the convergence analysis. So I believe it to be the case as well. But some of my students are working on it. They seem to think that it may not be a serious issue. We will have to see.
All right.
Yeah.
That's the spirit, right? That's the good attitude.
Yeah, that's right. Yeah, thanks for your question. Yeah.
Hello, one question.
Yes.
Could you please go back to page 12?
12. Okay. This one.
Page 12 is about the definition of the injective definition of this objective function. Yes.
Okay.
Here you define the arrow as a minimum of to ignore the group action.
Yes.
But my question